Alright guys, welcome back. In this example, we want to use the three-moment equation to draw the shear force diagram, bending moment diagram, and solve for the reactions of this statically indeterminate beam that's got some loads on it. So the first thing that we need to do is we need to identify that this beam has two spans. It's got span 1 there, and it's got span 2 there. So we're in the three-moment equation, we're going to be calling this A, B, and C, and then it's got this little overhanging bit here as well. That we're going to get to in a second. So the first thing that we want to do when we're doing the three-moment equation is we want to draw the bending moment diagrams for these spans with the applied loads as if they were simply supported. And then we want to calculate the area of each of these and the distances of their centroids out to the outer sides of those spans. Alright, so now let's go and write the three-moment equation. And this is the form that I like to write it in. I mentioned in the previous video that some people might use different subscripts, like I like to use A, B, and C. Some people use L, C, and R for like left, center, and right. Or instead of doing like length 1 and length 2, they would do like length AB or whatever. So again, just watch out for the subscripts there. This is just the way that I like to write it, but there's more than one way that you can do this. Okay, so the problem does state that EI is constant, and we do have an EI in every single term, so we can knock that out. And we're left with a bit of a simpler equation here. So the next thing that we want to do also is we have three internal moments. We have MA, MB, and MC. We actually already know two of them, or we can find out two of them. So when we look at MC, MC has to be equal to 0 because it's like it's basically at the end of a span there, and that would mean if you drew the free body diagram here of a virtual cut infinitesimally close to this reaction, you would see that there is 0 internal moment. And then for A here, we can actually find this as well. So if we do a virtual cut free body diagram, starting on the left-hand side and taking a cut just to the left of A, we have 20 kilonewtons pressing down on the end there. That means that our internal shear here is going to be 20 kilonewtons pressing up. And then we're going to have a moment. This is going to be MA. Counteracting that, and this distance here is 5 meters. So 5 times 20 for that force couple is 100. And so that's going that way. So yeah, the moment would be going clockwise to the right of a virtual cut, which is an opposite of our positive sign convention. If you remember from beam bending, we have positive sign convention. It is like this. All right, so we got opposite arrow to that. So we have negative 100 kilonewton meters. All right, MA is equal to negative 100 kilonewton meters. Cool, so if we look at everything in the equation now, we know length 1, that's 10 meters. MA, we have that. We don't have MB, and we have MC, we have L2, we have A and X, so we calculated those up here. So if we just come down a little bit, we can fill in some of these values. And then we can simplify this, so we'll get minus 1,000 plus 40 MB plus 0 is going to be equal to negative 1875 minus 2500. All right, and that all reduces to MB is equal to negative 84.375. And this is the internal moment at B. It's negative 84.375, just like MA is the actual internal moment at A, and MC is the actual internal moment at C, just if we're looking at the actual system along the span. So now what we want to do is we actually know the internal moments at 3 points, and what we can do then is we can draw a free body diagram of each span with virtual cuts just before each support. So when we label on our internal moments and our internal shears right at those cuts, those will actually be the internal moments at those points, or the shears right just to the right or left of those cuts. So here I've drawn on MA as positive 100 kilonewton meters going counterclockwise, and that is where did I draw that? That is going opposite of our positive sign convention. So that's why we go from negative here, we draw it in the negative sense and then write it in a positive value. It's the same thing. Here, this is negative because it's going clockwise to the right of a virtual cut. Same thing if we look at it from the other side. It's also negative, going counterclockwise to the left of a virtual cut. And then that magnitude is 84.375 negative kilonewton meters. And then here, MC, this is just equal to 0. Didn't matter which way we draw that. And then when we draw on the shears, we draw these on in the positive sign convention, or in the positive directions. So when we calculate them, if we get them negative, then that will actually be negative on the shear force diagram. And then also draw on the loads. So we have the concentrated load halfway along the span, and then the distributed load the whole way across the right-hand span, or span 2. And now we can solve for the shears by just doing the sum of moments about a point, and then the other shear by just doing the sum of forces in the y direction. So VB1, if we take the sum of moments about A, then we get it to be negative 23.4375 kilonewtons. And then if we do the sum of forces in the y direction, that's going to give us a VA is 26.5625 kilonewtons. All right, so if we do the same thing for the second span, we'll do the sum of moments about point B, and we'll find that VC is equal to negative 41.5625 kilonewtons, which means that's opposite to the way that we drew it, so it's actually going up. So if we have 100 pressing down from the distributed load, right, 10 times 10, and then we have this 41.5 going up, then that means when there's sum of forces in the y direction, that VB2 is going to have to be 58.4375 kilonewtons, and that is positive, so it is going in the direction that we assumed. It's going up. So now at this point, by doing this, we've actually found the internal moments at each end of these spans and the internal shears at each end of the spans. And so if we come back up here to the original drawing, we actually have enough information now that we can go and we can look at this and we can draw the shear force diagram based on what we just calculated the whole way along. And then from the shear force diagram, then we can calculate the bending moment diagram. And then also from the shear force diagram, we can observe or just kind of pick off what the reactions are. So I'm going to pause the video here and then join me in the next video where we're going to draw the shear force diagram, bending moment diagram, and solve for the reactions for this problem.